Section: Introduction. In this section, we discuss the advancements in natural language processing, particularly regarding models that can manage longer sequences. We note that a context window of 128,000 tokens enables large language models, LLMs, to perform complex tasks like answering questions from multiple documents and understanding code at a repository level. This capability is largely due to Rotary Position Embedding, RoPE, which has become the leading method for positional encoding in LLMs. RoPE's effectiveness stems from its rotational properties and the way it encodes relative positions, helping models avoid issues with out-of-distribution rotation angles. We explain that by adjusting rotary frequencies, we can map extended context position IDs to ranges that the model has already learned. This allows the model to understand the relative positions of tokens even in longer contexts with minimal additional training. However, training for long contexts is still challenging because memory usage increases significantly with context length. To tackle this, we use brain floating point, BFloat16, during training, which helps reduce memory requirements without greatly affecting accuracy. Despite the benefits of BFloat16, we discovered a significant problem. It disrupts RoPE's relative positional encoding, especially in longer contexts. This issue arises from BFloat16's limited precision, leading to cumulative numerical errors as the training window expands. In contrast, using BFloat32 preserves RoPE's encoding properties. Our observations indicate that this breakdown diminishes the advantages RoPE provides for long context training. We investigated the cause of this breakdown and found that the first token in the attention window plays a crucial role in the deviation. Current methods do not specifically address this issue. In the full attention mechanism, each token attends to all previous tokens, which leads to increasing deviations as the window size grows. Standard intra-document attention uses cross-document masking, breaking the large window into smaller ones, but this creates inconsistencies in positional understanding due to different position IDs assigned to the first tokens of each small window. We found that resetting position IDs to ensure consistency across windows improves long context performance, confirming that inconsistencies are a key problem. However, this approach also limits the model's ability to learn the full range of rotational angles unless the data sequences reach the maximum context length. To address these challenges, we propose AnchorAttention, a flexible attention method that enhances long context capabilities and speeds up training. The innovation of AnchorAttention is treating the first token as a shared anchor, always assigning it the first position ID. This allows it to be visible to all documents in the context window while keeping tokens from different documents hidden from each other. By sharing the initial token, we eliminate inconsistencies and enable the model to learn the full range of rotational angles from shorter sequences. Additionally, AnchorAttention reduces the number of tokens involved in attention calculations, which helps minimize numerical errors. Our experiments show that training with AnchorAttention consistently outperforms full attention, standard intra-document attention, and our improved intra-document attention on the long context benchmark ruler across various lengths. On real-world benchmarks like long bench, AnchorAttention enhances in context learning while maintaining the model's performance on general tasks. In summary, our main contributions include identifying that RoPE's relative properties are compromised under BFloat16 precision, recognizing the first token's role in this deviation, and introducing AnchorAttention as a practical solution for long context training that improves model performance and reduces training time significantly. Section Summary. In this section, we discuss the challenges of maintaining Rotary Position Embedding, RoPE properties in long context training with BFloat16 precision, which leads to significant deviations due to numerical errors. We propose AnchorAttention, a novel attention mechanism that addresses these issues by treating the first token as a shared anchor, improving long context capabilities and reducing training time while preserving model performance on various tasks. Section: Discrepancies in RoPE's relative positional encoding. In this section, we explore the discrepancies in RoPE's relative positional encoding. We begin by discussing the background of Rotary Position Embedding, RoPE, which is crucial for modern large language models, LLMs, that utilize the transformer architecture. A key feature of this architecture is the attention mechanism, where we define the attention logit matrix and the roles of query and key vectors. We note that positional embeddings are essential for understanding the order of sequences, and RoPE is widely used in LLMs. RoPE operates by dividing the query and key into two-dimensional chunks and rotating them at different frequencies, which helps in calculating attention logits based on the relative distance between tokens. We clarify that the rotation matrix is applied outside the Flash Attention 2 module, while the inner product of the key and query is processed within it, requiring a conversion to BFloat16 precision. We then address how BFloat16 precision disrupts RoPE's relative properties, particularly with longer contexts. Theoretically, RoPE should not be affected by adding a constant positional shift to every index, but we investigate whether this holds true in practice. We redefine the attention computation to analyze the effects of positional shifts and measure the differences in attention scores across various layers and heads. In our experimental setup, we vary one positional shift while keeping another constant and observe the differences in attention scores. Our results indicate that using BFloat16 precision leads to noticeable effects on attention computations, while this effect disappears with Float32 precision. We also find that pre-training amplifies these discrepancies. Furthermore, we analyze the attention differences for individual tokens, revealing that the first token significantly contributes to the overall difference. We extend our study to various sequence lengths and find that longer sequences exacerbate the discrepancies, particularly for the first token. In summary, we conclude that the discrepancies in RoPE's relative positional encoding become more pronounced with longer sequences and specific precision settings. Section Summary. In this section, we investigate the discrepancies in Rotary Position Embedding, RoPE, when using BFloat16 precision, revealing that positional shifts affect attention computations in pre-trained models, particularly for the first token, while this effect diminishes under Float32 precision. Our findings indicate that these discrepancies become more pronounced with longer sequences, suggesting a breakdown of RoPE's theoretically claimed relative positional encoding after pre-training. Section: AnchorAttention. In this section, we explore AnchorAttention. We previously showed that using BFloat16 precision affects the relative positional encoding of RoPE, especially as sequence lengths grow. Despite this, BFloat16 is still preferred for its computational efficiency, which is vital for handling long contexts. The best approach in these cases is to continue pre-training on long context data, but this is complicated by the quadratic computational cost of attention mechanisms as sequence length increases. To address the growing errors with longer sequences while keeping the benefits of BFloat16, we introduce AnchorAttention. Training a long context model usually involves processing long sequences, but this can worsen precision errors with BFloat16. We found that reducing sequence length could help, but it seems counterintuitive to train a long context model with shorter windows. To resolve this, we revisited existing techniques and discovered that using intra-document attention, which masks out attention across different documents, allows us to train a long context model with shorter sequences. This method has been successfully applied in open-source models like the Llama 3 series, and recent studies confirm that masking attention across document boundaries improves performance for both short and long contexts. We also questioned whether the discrepancies in RoPE under BFloat16 significantly impact long context performance. Given that intra-document attention seems to reduce these discrepancies, we hypothesized that the effects of BFloat16 might be minimal when using this attention type. To test this, we compared two positioning methods, one that assigns position IDs continuously throughout the sequence and another that resets the position index for each document. We expected both methods to yield similar results, and this comparison aimed to determine if the discrepancies in positional encoding lead to noticeable differences in long context performance. In our experiments, we trained a 128K model based on the Llama 2-7B architecture using the SlimPajama dataset with intra-document attention and evaluated it on the ruler benchmark. We compared scenarios with and without resetting position IDs to see how this affects model performance. Our results showed that resetting position IDs consistently improved long context performance, while not resetting them led to poorer outcomes. This performance gap likely arises from inconsistencies in position IDs assigned to the first token of each document. By resetting position IDs, we maintained a consistent positional relationship, which is crucial for the model's understanding. We also introduced a shared anchor token for efficient long context training. While restarting position IDs improves performance, it limits the model's ability to learn the full range of rotational angles unless it processes sequences that meet or exceed the context length. This limitation makes it difficult to generalize to longer contexts due to the scarcity of lengthy data. To tackle this, we proposed AnchorAttention, which includes a shared anchor token visible to all documents within the long context window. This design helps the model focus on coherent information by ignoring redundant attention connections across documents. In AnchorAttention, the anchor token serves as a common starting point for all documents. We observed that the first token significantly influences deviations in relative positional encoding. By using a shared anchor token with a fixed position ID, we eliminate confusion about the relationship between the start of a document and the position ID. We designate the beginning of sequence token as this common anchor, which minimizes the impact of any precision errors from BFloat16. This approach allows us to use continuous position IDs throughout the window length, enabling the model to train on the full range of rotational angles without relying heavily on abundant long sequences. This reduces the need for collecting and upsampling long sequence data, making our method a powerful solution for long context training. Section Summary. In this section, we propose AnchorAttention, an innovative attention mechanism that utilizes a shared anchor token to enhance long context model training while addressing precision issues associated with BFloat16. By maintaining continuous position IDs and focusing on coherent information, our approach allows for effective training without the need for extensive long sequence data, ultimately improving model performance. Section. Long Context Extension Protocol. In this section, we focus on optimized training strategies and robust evaluation metrics, detailing our choices for base models, the long context training dataset, specific training configurations, and the benchmark setup. For our experiments, we primarily use the Llama 2-7B model as our base model. To evaluate the effectiveness of our proposed methods, we also assess Llama 3-8B, QWEN 1.5, 1.8B, and Mistral 7BV0.3. These models represent various architectures and pre-training methods, allowing us to test the generality of our approach. We utilize the Slim Pajama dataset for long context training, which is an open-source version of the Llama pre-training data. This dataset includes a variety of text sources like Common Crawl, C4, GitHub, Archive, Books, Wikipedia, and Stack Exchange. We also apply a data mixture method that increases the number of long sequences while keeping the original dataset's distribution intact. This upsampling helps the model better handle long context scenarios during training. We sample 2 billion tokens from both the original and upsampled Slim Pajama datasets, referring to them as SLIMPAJAMA64K and SLIMPAJAMA128K based on their sequence lengths. The upsampled dataset is called UPSAMPLEDMIX128K. Our training hyperparameters are based on established guidelines. We train all models on 8 NVIDIA A100 GPUs, setting the learning rate to 2 × 10⁻⁻5 and using the Atom W optimizer with a weight decay of 0.1. We train each model for 2,000 steps, which is about 1 epoch over the 2 billion token dataset. The batch size is set to 8, translating to 0.5 million tokens per batch for 64K context and 1 million tokens for 128K context lengths. To effectively evaluate our proposed attention mechanism's impact on long context capabilities, we emphasize the need for robust evaluation metrics. While perplexity, PPL, is commonly used, recent studies suggest it may not reliably assess long text understanding. PPL tends to focus on local information, which can overlook important tokens necessary for understanding long context inputs. We also found that increasing long data improves PPL, but relying solely on long data can hurt downstream performance. Our observations indicate that while PPL remains stable after initial training steps, performance on the ruler benchmark continues to improve, suggesting PPL may not accurately reflect enhancements in long context performance. Existing benchmarks for long context models, like Helmet and Long Bench, often focus on instruction following abilities, making them less suitable for evaluating our models. Tasks in Long Bench can be managed with a context length of 16K tokens, which does not fully challenge models capable of handling 64K or 128K tokens. Despite these limitations, we still evaluate our models on Long Bench due to its inclusion of real-world long context tasks and its few shot-in-context learning tasks, which are relevant for assessing base models. To thoroughly evaluate our model's long context capabilities, we use the ruler benchmark, designed for extensive context lengths. Ruler assesses abilities such as locating specific data, tracing relationships, aggregating information, and distinguishing relevant details in complex queries. It includes various tasks that accurately represent the capabilities of models like ours. However, we exclude two tasks for the Llama 2-7B model based on its struggles with these tasks in its original context window, as we believe it is unreasonable to expect the model to perform better in extended contexts. For other advanced models, we use all tasks in the ruler benchmark. We recommend reporting the average ruler performance across 5 checkpoints to provide a more reliable assessment, rather than relying on a single checkpoint. This approach helps avoid cherry-picking specific results. To ensure that continual pre-training maintains the model's core abilities, we use the MMLU and HELA-SWAG benchmarks. MMLU evaluates knowledge and reasoning across various subjects, while HELA-SWAG tests common sense reasoning by asking models to choose the most plausible scenario continuation. We observe minimal performance differences between base and chat models, confirming their suitability for evaluating foundational abilities. Section Summary. In this section, we detail our optimized training strategies and evaluation metrics for long context models, using the Llama 2-7B as our primary base model and the Slim Pajama dataset for training. We emphasize the importance of robust evaluation metrics, such as the ruler benchmark, to accurately assess long context capabilities, while also ensuring that our models maintain their foundational abilities through established benchmarks like MMLU and HELA-SWAG. Section: Optimizing Positional Embeddings for Long Context Training. In this section, we explore how to optimize positional embeddings for long context training. We trained the Llama 2-7B model using the SLIMPAJAMA 64K dataset, breaking it into sequences of 64,000 tokens. We tested 3 methods: RoPE, NTK-aware, and YARN. We adjusted the base value in the embedding formula, which relates to the RoPE theta parameter in transformers. The NTK-aware and YARN methods rely on the relative scale, which we set to 16, based on the original context size of 4,000 tokens and the new size of 64,000 tokens. Following previous research, we used 1 billion tokens for training to balance time and model evaluation. Our results, shown in a table, indicate that the standard RoPE with an appropriate base value performs best within the training context length, surpassing NTK-aware and YARN methods at 64,000 tokens. To assess performance beyond the training context, we evaluated the models on the 128,000 token ruler benchmark. We found that YARN embeddings generalize better to longer, unseen contexts, while standard RoPE performs well only within the trained length and declines in performance at longer contexts. Recognizing the significance of the RoPE base value, we further examined the selection of RoPE theta by training models with a context length of 32,000 tokens to conserve resources. Our findings, presented in a table, show that performance peaks at a specific theta value, with minimal gains beyond that and slight declines with higher values. Based on this, we adjusted the base theta values for different context lengths: 1 million for 32,000, 5 million for 64,000, 10 million for 128,000, and 50 million for 256,000 tokens, ensuring optimal performance across various lengths. We also discussed the importance of positional embedding in transformers for capturing the order of input tokens. Early methods struggled with longer sequences, leading to the introduction of relative positional embeddings. Recently, Rotary Positional Embedding, RoPE, has gained popularity for its ability to extend context length with little fine-tuning. We also look into how the precision of BFloat16 might affect the relative position properties of RoPE. While training-free methods have shown potential for extending context lengths, we note that additional training specifically for long contexts yields better results. Long context training presents challenges, such as quadratic computational complexity and performance drops beyond pre-training lengths. Various strategies have been proposed to tackle these issues, including modifying RoPE and adjusting attention patterns to focus on the most relevant parts of the input. Other techniques aim to reduce computational complexity, such as sparse attention and group query attention. To address hardware limitations, methods like sequence parallelism and optimizations like ring attention and deep-speed Ulysses have been developed. Our work adopts a continuous long-context training approach with efficient implementation, focusing on attention design to address issues related to RoPE and BFloat16 precision.